it's not the answer in its current form. Okay, it might be leading to the right answer, but it's not the answer yet. We don't have a rigorous working model of that, although scientists continue to work on it. I think the answer may involve the one-way speed of light. I'm going to give you what I think is the answer, and it's, like, I can't prove it in an absolute sense, but I think the evidence is compelling. The solution may involve what we call the one-way speed of light. This is a complex issue, so put your thinking caps on here. Physics is complicated, to say the least. The speed of light is 186,282 miles per second. It's fast, and we abbreviate that by the letter c, a lowercase c. But that is a round-trip average speed. And what I mean by that is you've measured the speed of light by having it travel in two directions and then taking an average. And so, for example, if we wanted to measure the speed of light, what we could do is we could get a really long hallway, a hallway that's 186,282 miles long. We'll pretend we have government funding so we can waste it that way. And we'll put at one end of the hallway a flashlight and a clock, and at the other end we have a mirror. And at exactly noon, we turn on the flashlight for a split second, sending out the light pulse, and then what happens is that light pulse bounces off the mirror, comes back, and as soon as we see the reflection, we look at the clock. And you would find, if you did this, it would take 2 seconds. If the hallway were that long, that's how long it would take. It would take 2 seconds to do that every time. And so the total distance, which is 186,282 divided, well, times 2, because it has to go there and back, divided by the total time of 2 seconds, will give you the average speed of light. But it's an average speed, because we don't know that light actually takes the same time to go out as it does back. It could be the case that the light actually zips out and then maybe it zips out instantaneously and takes all of 2 seconds to get back. Maybe the opposite. Maybe the light travels out very slowly and then zips back instantaneously. You see, we don't know. Either way, you get 2 seconds. Take a look. They're emitted at the same time, and the light returns at the same time. Either way, you get 2 seconds. Maybe it's the same speed. Maybe it's very different. And people say, well, why would it be different in different directions? I don't know. Why would it be the same? Right? That direction is not that direction. They're different. It could be different. And there are substances where the speed of light is very different in different directions. Maybe the universe is such a substance. The point is we don't know. And so we're going to have to do an experiment to find out, right? We're going to have to measure the one-way speed of light. How would you do that? Well, you'd need 2 clocks. You can't use a mirror because we just want a one-way trip this time. So we're going to put 1 clock at that end, 1 clock at that end. We'll send out the light pulse. Let's say when this clock is at noon, we send out the light pulse, and then when it hits this other clock, we read the time. Right? And you're thinking, yeah, it'll be 1 second. Yes? Well, I tried this in my office. I don't have a long hallway. We're a ministry. We don't get government funding. So when my watch hit noon, I turned on the flashlight, and there's a phone over, there's a clock over by my phone. And right at noon, and I looked, and as soon as I saw the light on the clock there, it read 12:05, and I said, it takes 5 minutes for the light to get from my watch to the clock. You're not buying that, huh? What did I do wrong? I assumed that the 2 clocks were synchronized, right? In other words, the clock by my phone is obviously 5 minutes faster than the clock on my watch. The 2 clocks have to read the same time at the same time. They have to be synchronized. No problem, we'll make sure the 2 clocks are synchronized. Turns out that's really hard to do. 2 clocks that are separated by a distance, in fact, you cannot do it exactly. And I'll show you why. Now, you might think, well, I've got a clock that synchronizes itself. In fact, this watch actually receives a signal from Fort Collins, Colorado, and it synchronizes it to the atomic clock in Boulder. It does that every night, so I never have to set it. It's really neat. But so that's what we'll do, right? We'll put a radio transmitter at one of those clocks, and when the clock strikes noon, we'll send out the radio pulse to the other clock, yes, and then we'll set it to noon. But there's a problem, because the radio pulse, even though it's fast, it takes a little bit of time for the radio to get from one clock to the other. So if you just did that, it would be just a little bit behind. My clock is technically a little bit behind the one in Boulder. It's a fraction of a second. I don't worry about it. But here we got to do it exactly if we're going to measure the speed of light. Now, we could compensate for that if we could set this clock a little bit forward if we knew how long it took the radio pulse to get there. How fast does radio travel? It travels at the speed of light. We know that because if you turn on a radio transmitter and a light pulse, they'll hit the wall at the same time. We know they're the same speed. We know that. But you see, the one-way speed of light is the very thing we're trying to measure. That's the thing we don't know. So you can't do it that way. Now, some people have for some reason thought the problem would be solved if you put the radio transmitter in the middle. They say that way you send out the beam, and then they're set to the same time, and it doesn't matter what the delay is. Pretty clever. Except that assumes that the radio pulse and therefore light travels the same speed that way as it does that way, doesn't it? If light and therefore radio travels at a different speed, then that clock's set to noon first, and then that clock's set to noon second. See, so putting the radio transmitter in the middle doesn't solve the problem. Or if you use electricity or any other thing, it's all dependent on the speed of light anyway. There's one other thing we might try, and that is we'll take the two clocks, put them in the same place, and synchronize them. That we can do. And then we'll move one of the clocks, or both of them, to the opposite ends of the hallway. Should work, right? Because they're definitely synchronized when they're together. We can see that they read the same time at the same time. But there's a problem. Because according to Einstein, motion affects the passage of time. The very act of moving the clock causes it to become desynchronized from the other one. Isn't that interesting? Now, there's an equation that tells you how much it's desynchronized, and so then you could adjust it. But guess what's in that equation? The speed of light. Yeah, the very thing we don't know. Apparently, you can't do it. And by the way, don't come up to me and say, I've thought of some way by which you could measure the one-way speed of light, unless you've read 10 papers on the topic. Because physicists have been trying to figure this out for 100 years, and nobody's been able to do it. And so I want to make sure you're familiar with literature, because everything you can think of, I guarantee you it's been tried, and it doesn't work. There's some catch you haven't thought of. It's like perpetual motion machine. Apparently, it is impossible to synchronize two clocks at a distance without knowing the one-way speed of light. And, of course, you can't measure the one-way speed of light unless you have two synchronized clocks at a distance. Okay? It's a catch-22, as it were. There is no way to measure the one-way speed of light. Can't be done. So what does that leave us with? If it can never be measured, the best we can do is pick what we want it to be and stick with it. And that's exactly what physicists have done. We've decided we like it to be the same in all directions because it makes the math easier. But you don't have to pick that. If you pick it different directions, that'll work just as well. And so what we do is we say, well, we're going to decide it to be the same, and that's how we'll synchronize clocks, okay? And so when the lightning bolt strikes, the light goes out from it, and when the clocks see the light, they're set to noon. And we're going to call that synchronized. You can do that. And if you measure the one-way speed of light, you'll find, using this system, you'll find that it's the same in all directions. But if you assume it's different in different directions and you synchronize your clocks that way and you go about your one-way speed of light measurement, you'll find it's different in different directions. Whatever you pick, your experiment will confirm. And so you see, it's a convention, like driving on the right side of the road. It's something we all agree to it, and it works. But you can pick another convention. You can go to Australia, and they drive on the left side of the road, and that works just as well. That light requires the same time to traverse the path A to M as for the path B to M is in reality neither a supposition nor a hypothesis about the physical nature of light, but a stipulation which I can make of my own free will in order to arrive at a definition of simultaneity. It's something we get to pick out of our own free will. And that was something that was recognized by Albert Einstein. Einstein knew that you can't measure the one-way speed of light. It's something that you get to choose. And we've seen that confirmed many times since. So here's what I'm going to do. I'm going to choose this convention. We're going to call it the anisotropic synchrony convention. Anisotropic means different in different directions. So I'm going to let the speed of light be infinite when it's moving toward me, and half c when it's moving away. Because the round-trip speed is set by God. You can't change that. That's 186,000 miles per second. And so if it's infinity toward me and it's half c away from me, that averages out. People wonder why you average infinity with a half c and get c. But it's because it's a time average. And it takes no time for the light to get here. But in any case, that's the way it works out. Now, when it's in other directions, it'll have different speeds. Now, why would I pick this convention? There's two reasons. One of them is because this is the way all ancient cultures implicitly did it. Because they did not subtract off light travel time because they didn't know what the round-trip speed of light was anyway. When you see something, that's when it happens. If you use this convention, when you see something, that's when it happens. Isn't that neat? Second reason is it solves the distant starlight problem. I think that's a pretty good reason. So, under the anisotropic synchrony convention, light takes no time at all to get from distant galaxies to here because of the way we've chosen to synchronize clocks. It's not a problem. So the distant starlight problem is solved if the Bible uses this convention. And in my opinion, that's the only thing that is really uncertain. And I don't think it's all that uncertain, but if there's a weak link in my argument, this is it. I'm proposing that the Bible uses this anisotropic synchrony convention because that was the ancient way of doing it. Okay? And I think it's implied in Scripture as well, because the Bible says, God said, let there be lights in the expanse of the heavens to separate the day from the night. Let them be for signs and for seasons and for days and years. Yes? And we find that those are the sun and the moon, the stars also in verse 16. It says, and let them be for lights in the expanse of the heavens to give light on the earth. So one of the purposes of the stars was to produce light that falls on the earth. And it says, and it was so. What was so? God made the lights, and their light fell upon the earth, you see. And so it seems to me the Bible is suggesting, and this is an inference on my part, but it seems to me the Bible is suggesting that God made the stars and their light fell on the earth right away, which is the anisotropic synchrony convention. And so I think that Scriptures at least suggest that. I could be wrong about that, but I think that's a very plausible solution to distant starlight. In any case, the critic would have to argue that he knows the Bible's using Einstein's synchrony convention, and therefore, in order for there to be a problem. And I think that's going to be a real difficulty for him to prove that. So we've seen that the Bible is right when it speaks about the glory of God being revealed in the heavens. The Bible's right when it talks about the basics of astronomy. It's right when it talks about the age of the universe. It's right when it talks about the uniqueness of the earth. And it's right when it talks about distant starlight. There's not a problem. And folks, we need to know this information because there are people that are right now on their way to hell because they are convinced that the Bible's been disproved scientifically. And we need to get this information in our heads so that we can defend the Word of God effectively. And that's what we're all about here at the Institute for Creation Research. We really want people to be saved, and we're not bashful about that. We're different than the ID movement, who leaves out the Creator, and they have a strategy for that. I understand why they do that, but we want people to be saved. We're very happy to tell people who their Creator is. And that's why we produce these resources. Let me show you some of the resources we have here at the conference. I've got a book called Taking Back Astronomy, which covers the information that I just covered, basically. And it goes into some things that I didn't have time to hit today. And it's beautifully illustrated. It's got some of these wonderful Hubble images in it. And I think that's one of the ways that the universe declares God's glory. So I'd encourage you to get that. It makes a really persuasive case. It's not a thick book, but it makes a very persuasive case that you can trust the Bible when it touches on astronomy. And therefore, you can trust it in other issues as well. My latest book on astronomy, The Stargazer's Guide to the Night Sky, it's not an apologetics book. It's just a book on how to enjoy the night sky from a creationist perspective. And I think that's the best way to enjoy the night sky, is to know the creator of the night sky. And this book's going to show you how to find the various objects that we looked at. A lot of those you can see in a small telescope if you know where to look. Some of them you can see with your naked eye if you know where to look. You just have to find the star charts. You don't need expensive equipment. Just with your naked eye, it'll show you how to find constellations, bright stars, things like that. If you have binoculars, it'll show you star clusters that you can see in binoculars. You can see Saturn's rings in binoculars. Jupiter's moons you can see in binoculars. You just got to know where to look. And this book will show you how to do that. If you've thought, well, I'd like to get a telescope, but I don't know what kind. Well, this book will tell you about different kinds of telescopes and price ranges and what kind you might want to get. Got all that kinds of information in it. It's a great book. I'm really happy with it. It's beautifully illustrated. There are full color star charts and the like. And so I hope that hope you'll take a look at that. The Ultimate Proof of Creation. If you really want a powerful book on how to defend the Christian faith, this is it. If you get one book at this conference, I'd encourage you to get this one, because this is going to show you how to powerfully defend the Christian faith. You know how Jesus, in his earthly ministry, the Pharisees and Sadducees would come to him trying to trip him up, trying to trick him, and his answer was just so perfect. He just turned around on them, and then they didn't know what to say. Wouldn't you like to learn to think like that? You can. And this book really is training you how to do that. Not that I've mastered it, but I've learned a lot over the years about how to answer the critic. And this book is really going to train you how to think biblically, how to think logically, as it were. Check us out as well, our website, icr.org, and our new website that we're just launching. It's still very preliminary, youroriginsmatter.com. And that's a great way that you can participate in this conversation. So thank you very much.